Welcome, students. Today we're going to look at parabolas, which we've seen before a couple of times. However, we're going to focus on them as geometric objects instead of just graphs of functions. When we learned about circles, we knew that there was a geometric definition of a circle. A circle is the set of all points that are a given distance away from the center. And there's also a geometric definition of a parabola that we haven't seen yet, and so I want to talk about that now. A parabola is the set of points in a plane that are equidistant from a fixed point F, called the focus, and a fixed line L, called the directrix. And we can see that in our example here. We have our example parabola, and we have the focus or focal point drawn in, and then also the directrix. And if you look at any point on the parabola itself, the distance between that point and the focal point is equal to the distance that we need to go down from that point to the directrix. In other points, those distances will be greater, but we notice that the distance from the focal point to the point on the parabola is the same as the distance from the point on the parabola down to the directrix. And the same is true here. This distance, which I didn't draw in nicely, but there you go, is equal to this distance. We could even put in little markers if we wanted to show which distances are equal to each other. And the same thing is true if we look at the vertex. The distance from the vertex up to the focal point is equal to the distance from the vertex down to the directrix. So this is a geometric property that defines a parabola, similar to how circles were defined by a geometric property. Circles were the set of points a given distance away from the center. A parabola is the set of points that are equidistant between a fixed point and a fixed line. Now, when we talked about parabolas previously, we saw that we could get a parabola by looking at the graph of a second-degree polynomial equation. So something like y equals x squared, or y equals negative 3x squared plus 2x minus 1. We've seen that there are shapes that are maybe a little bit similar if we look at fourth-degree polynomial equations or sixth-degree polynomial equations. And sometimes students even call these parabolas, but they are not in fact parabolas by the geometric definition. We don't have this same property of equidistant points if we were to look at the graphs of these functions down here. So when we looked at parabolas previously, there were two kind of standard forms that we saw for a parabola. We've got y equals ax squared plus bx plus c. And we've also seen y equals a times x minus h squared plus k. Remember, in this case, h comma k gave us the vertex of the parabola. But now that we've learned the geometric definition of a parabola, we're not just going to want to deal with the vertex, we're also going to want to be able to look at the focus and the directrix. So we're going to look at a new form for parabolas that's going to be different from these two over here, and it's going to focus on the focus and the directrix. Now, to get this, we're actually going to have to do a little bit of algebra, and it's going to get a little bit ugly, but once we finish the algebra, we're going to get a nice, simple formula that's going to help us look at some parabolas given the focus and the directrix. So let's get into some calculations. Let's take a look at a parabola whose vertex is the origin and whose focus is at the point 0, comma p. So p units above the vertex, p units above the origin. Now, what that means for us is that the directrix is the horizontal line that has equation y equals negative p, because we know that the distance from the focus to the vertex has to be the same as the distance from the vertex down to the directrix, and both of these distances are p. So once we know the focus and the vertex, we can figure out the directrix. Now, I want to look at any point on the parabola. We'll call the generic point on the parabola P with coordinates x and y. And we know that something has to be true about this point. Specifically, the distance from the focus to this point has to be the same as the distance from the point down to the directrix. Now, it is likely that whenever I do these drawings, these distances won't look the same. And this is because I'm not a robot that can draw perfect parabolas. My parabolas are not going to be perfect, and so they're not going to look exactly like we would want. But this is what we know must be true. These distances have to be the same if we've drawn a true parabola. And so we can actually use the distance formula to figure out what these two distances are. So if we wanted to know the distance between f and p, remember, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. So if we look at the distance between f and p, the difference in the x coordinates is going to be x minus 0, which is x. So that's going to be x squared plus, and then the difference in the y coordinates is going to be y minus p. So that's going to be y minus p squared. So this represents the distance from f to p. And then the distance from p down to the directrix is going to be y plus lowercase p, because y is the height of this point, and then lowercase p is how far beneath the x-axis our directrix is. So this is going to be equal to y plus p. And what we're going to do here is we're going to square both sides, and we're going to do a lot of simplifying, and we're going to end up with a much simpler relationship between x, y, and p. If we square both sides, that gets rid of the square root on the left-hand side. And then on the right-hand side, this becomes y plus p squared. If we go through and actually square these using either foiling or the special product formulas, we get y squared minus 2py plus p squared on the left. And on the right, y squared plus 2py plus p squared. And we notice that there are y squareds and p squareds on the left and right. If we subtract them, they will end up vanishing. And so we're left with x squared minus 2py equals 2py. And if we add 2py to both sides, we end up with a simple version of this relationship, x squared equals 4py, or x squared equals 4yp, doesn't matter. Either way, this is the formula for a parabola with center at the origin and with focus at the point 0, p. In the next video, we're going to look at a couple of examples of parabolas, looking at the focus and the directrix and looking at this formula so we can get a little bit more comfortable with it.